All right, it's now time to wrap up the topic of inheritance. We have talked about many topics since 2 weeks ago, and let's recall very quickly. Remember, we started off by talking about the two alternative designs to inheritance without using inheritance, and we evaluated them using the two design principles, single choice versus cohesion. And when we actually want to implement inheritance, we have to use the super keyword and extends keyword. And then we dive deeper into talking about static type, expectation, dynamic type, polymorphism, dynamic binding, and also typecasting. And for typecasting, we talk about two stages, either for compilation, whether or not it will compile, and also at the runtime, whether or not we'll run into a class cast exception. And then for this week, we spoke about how we can apply polymorphism for method parameters, and then how you can apply polymorphism in method return types. And also for both cases, we really try to construct a polymorphic collection or polymorphic array. It's so important for you to really try to synthesize all these topics together. And for this video, I just want to summarize the rules that will be very practical for you to really apply for your further endeavor, about OOP. Not just for this course, but definitely beyond this course as well. I want to mention the rules. And then I want to touch upon briefly the equals method and toString method. They are just some special cases of overridden methods that you want to watch out for. And then we're done. And I'll suggest some activities that you really want to complete on your own beyond this lecture. Okay, let's now start with just some quick reminder about static type versus dynamic type. Which one to consider and when to consider which. Whether or not Java code compiles, you should really only worry about static types. If the question is about whether or not a line of code is actually going to compile, you only consider static type, okay? Because inferring dynamic type from the compiler is actually an undecidable problem. Remember the A+ challenge I posed to you, right? It will never be implementable. All right, so when should you look at the dynamic type? So the behavior of Java code being executed at runtime. For example, let's say two very common scenario you might be asked. Which version of the method is going to be called, and also whether or not a class cast exception will occur for a typecast. In that case, you have to look into the dynamic type for the answer. Okay, and of course, whenever you want to track the dynamic type, it's an undecidable problem to automate. So the best practice will be to visualize how exactly objects are being created, and also the variables are reassigned by drawing arrows, of course. Okay, so that's the first point I would like to remind you about. And this table here looks very dry and also tedious, but I think it's a very valuable table actually for you to really understand. So this one really synthesize everything together. Be a little bit patient. Let me try to go over with you. Let me just tell you what the structure for the table. We got two columns. So the first one is about the code structure you might write into in your OOP. And the right hand side here is very important about what does it really mean for the line to compile to be valid. Okay, we'll consider different cases. May not be exhaustive, but I think that should be the common ones you'll write into. The first one just about variable assignments. The second one will be about some method call, and then we assign the return value of some method call to another variable, and then we try to cast a variable, and we try to assign the cast into another variable, and we try to cast something and then pass that as argument to some method call. Right, so these are the cases I would like to talk about. For each one of them, what does it really mean for that particular line of code to be valid or to compile? Okay, let's now take a look. You can also read through the description in the table. The same table over here, I just want to guide you through the table together, right? So you're not the only one who suffer. I suffer as well by going over them with you. Okay, but it's going to be beneficial. Okay, let's take a look. Okay, so let's now start with the first line. If I want to judge whether or not a substitution is going to be valid, I want to see if the right-hand side static type is the descendant class of the static type of the left-hand side, right? So that's what I need to look at. So is Y static type a descendant class of X static type? That's what we have spoken about. That one should be rather straightforward. Okay, so let me just say that. Okay, the next one. What if I want to do a method call over here? I want to use a dot notation. And we know that it really depends on the context object static type. Okay, so this is the context objects. Let me just draw that more perfectly. Okay, so this is the context objects. So there are two parts over here. Number one, we want to make sure the method M is really can really be expected by the static type of the context objects. So that's why the first one is method M defined in X static type, right? That's really important. X is static type. And the second one is about passing the arguments. You want to make sure the static type for Y is a descending class of the corresponding parameter static type, right? That's what we just spoke about this week. The two things over here. All right, let's now see this particular line over here, right? You can see this line, this part here is something we just said earlier, right? Let's just go over that quickly. So number one, you want to make sure the dot notation is valid. And also you want to make sure the argument passing over here is also valid. And number three, you can see this part here is really about what we just spoke about over here. You want to make sure the return type is a descending class, is a descendant of the static type of Z over here. That's also very important. Okay, so that's over here. Okay, let me just say one more thing here. So in this case, it's a little bit, it's really worth noting about the return type. Okay, return type. The static return type of this method M must be a descendant of the static type of the assignment target Z. All right, let's go on. And then we talk about typecasting, right? So you can see here, we are trying to cast Y into the type C. When should that be valid? It can either be an upward casting or downward casting. So C should be either an ancestor or descendant class of Y static type, right? And let's see this line over here. This part here is just like this. So that means we still have to make sure this is actually a valid cast over here. And then once we actually cast Y into C, the cast expression over here has the static type of matching the cast type, which is C. So now when we want to assign some expression of static type C into X, what should be the validity rule? That should be corresponding to this, the first one we spoke about. So that should be here, right? So that one there should be to make sure that is C actually a descending class of the static type of X. Is the static type of this a descending class of this static type? Finally, if you try to do, let's say this line over here, you can see this part over here is already like a valid cast, right? Let's do one by one. You can see this one is the most complicated one. You can see how many things your Java compiler in Eclipse is trying to do for you. But for you as a scientist or engineer, you should know what's really being checked for you. Okay, let's do one by one very quickly. Let's now start with the cast. Okay, so for this cast to be valid, C must be either an ancestor or descendant class of the static type of Y. Number one. Number two, since we are trying to pass, this is an argument, right? Since we are trying to pass, so you can see this part here, this expression is being passed as arguments. So that's why we have to make sure the arguments over here, the whole thing over here, is that, okay, so the whole thing over here, this one here, okay, is that a descending class of the parameter, of the corresponding parameter, right? That's number two. And even before that, you want to make sure the dot notation is even valid. How do we make sure that? To make sure that, you want to make sure is the method M defined in the static type of X, right? So to call this M on X, you want to make sure the context object X, its static type supports as part of its expectation N over here. Right, so these are all the rules I summarized for you, and I want to give you one exercise to do. All right, I think one exercise for you to do. What will be the validity rule? What will be the conditions under which the following line will compile? So let's say exercise. This is something I found that's simply just missing from the table, but I think it will be worthwhile assigning that as an exercise for you. What if we got this? Let's say Z is assigned to the following: X dot M, and then cast Y to C. When under what circumstances should this line be valid? So that will be your exercise over here. Alright guys, complete this exercise following the same manner as I did, for example, for each of the rule, and then hopefully that will help you understand the table better. You don't need to memorize anything here, but I'm just saying that whenever you see the different construct over here, you want to recall the story that we told in the earlier parts for the module about inheritance. You can see this these constructs simply summarize everything that we have spoken about syntactically. Okay, and one more thing to say. You can see when we try to do the cast over here, we are not actually trying to talk about runtime class cast exception, right? We only talk about type checking. Type checking only happens at the compile time, right? Only at the compile time, before the execution of your code, compile time. Okay, but there's one thing I would like to remind you quickly, okay? So for this cast over here, we learned about, we know that it's going to compile if it's either an upward casting to ancestor or downward casting to some descendants. But let's say it compiles. Where will we run into some class cast exception? Okay, class cast exception at runtime. If, well, I would suggest you pause the video and tell me what this is before you see my answer. Assuming that you thought about it, it will be a class cast exception if, at the runtime, if dynamic type of y is not a descendant class of, it's not a descendant of C that we are trying to cast into. If you cannot, because if the dynamic type of y is not the descendant class of C, that means it cannot fulfill its expectation. So that means the cast will simply fail at the runtime, right? That's something we spoke about last week. All right, study this table very carefully. I really hope that going over that with you will help. Okay, all right. Let's now move on to talk about equals method and also the toString method. Let's start with the equals. So this is the part that we talk about. Every class implicitly has a child, is a child class or subclass of the object class, right? We spoke about this already, this bullet point in the equals method lecture, right? I'm just repeating that. All right, so we know that this is default version of the equals method, right? So basically, for any subclass we declare in our hierarchy, if somehow the overridden equals method does not exist, it is possible we just have to invoke this default version. That's the point of the example I'm going to go over with you. Okay, and I want to say also there's another method in the object class called the toString method, which we have been also doing in the labs and also the tutorial. Right? I'll go to the toString method a little bit later. Okay. Very often you define your new classes, you just want to redefine or override the inherited definition for equals and toString. You just want to override them because the default behavior for the equals is simply to compare references between the context objects and the other objects. And the default behavior for toString method, do you remember, is only going to print out the addresses for objects, which may not be very useful. So that's why we want to override them. Okay, let's talk about the equals method first. Let me go over some principle with you, and then let's see some example to concretize the idea. All right, so objects, and let's say every class inherits the default version of the equals. Of course, you can choose to override it. Okay, let's say we have a reference variable v that has a dynamic type d. Okay, and let's say we got different cases, 3 cases in total. Case number 1, if the dynamic type d simply overrides the equals method, so that means because of dynamic binding, when you say v.equals, it's only going to call the overridden version of equals that's in class D, which is its dynamic type. That case number 1 is very straightforward. Case number 2, let's say D, the dynamic type, does not override the equals method. In this case, what's going to happen at the runtime, which I will illustrate to you, is going to go over the ancestor path for the dynamic type D, and to see which of the earliest ancestor actually overrides the method, if any. So, in case at least one ancestor classes of D, the dynamic type, overrides the equals, in that case, we will simply go up in the inheritance hierarchy all the way to the root of the hierarchy, right? If there's one, in that case, when we say v.equals, we're going to invoke the ancestor version. Otherwise, if there's simply no ancestor actually overrides the equals method, we will simply have to call the default version that's defined in the object class, right? That's conceptually. but I'm gonna exemplify all the cases for you. Okay. Hey, it's very important to say the same principle is gonna apply to the toString method. So once I illustrate to you about the equals method, you should really try yourself about developing similar example for the toString method. That's my hope. All right. Let's now take a look at the equals method. I got 3 cases for you. Okay, let's say for case number 1. Let's say we got in all cases, in all the 3 exercises, we got class A, class B, class C. You can see objects is the implicit ancestor for all of them. A is on the top, and B is the child, C is a grandchild. All right. So you can see A, B extends A, and also C extends B over here. Let's consider the following fragment of code over here. We got C1, we got C2, right? And then we try to invoke C1 equals C2. We want to know which version of the equals method will be invoked. According to dynamic binding, what's really important is the dynamic type for the context objects. Okay. So all you want to ask will be over here, what's the dynamic type of context objects C1? It is C. In that case, C is over here. Does C actually override any equals method? It does not. You can see this one, okay, here it does not override. Does not override the equals method. How about its parents? No, not overrides. What about its further parents, like a further ancestor? So now we're kind of in the root of the inheritance hierarchy, also not override. So that means, in this case, the only version that will be available to C will be the default version that's actually inherited, right? That's important. That's the points about the first exercise over here. So that means it's simply just going to be inherited to C. All right? So which version? Object version, the default version. That's exercise number 1. Let's take a look at exercise number 2. Very similar setup, and we're still looking at this line over here. C1 equals C2, right? You can see the version of the equals method depends on the dynamic type for C1, right? So we're going to see what's the dynamic type. It should be C. All right, it should be C. And now, in C here, we just got one overridden version of the equals method. Awesome. So that will be the one to actually call upon directly. Right? So this is the overridden version. We explicitly redeclare the equals method. Of course, they should be public. I'm just omitting that. They should be the public Boolean equals and then objects obj redecoration, and then you can put whatever you like inside the body of the implementation. So that's why the version that's going to be called will be the C version, which is over here. All right, that's case number 2. What about case number 3? Let's take a look. For case number 3, you can see we got a default version over here, and also we got some overridden version along the ancestor path, because the dynamic type, as we'll see, is simply just C. Let's see. So we are still calling C1 equals C2 over here, the context objects over here, right? Okay, context objects. What's its dynamic type? It is C over here, as we can see. So it will be just C. So you can see that's dynamic type over here. So the version of the equals method in dynamic type C should be called. So now, should it call this one over here, or should it call this one over here, right? You should really call the earliest one. The earliest ancestor that actually overrides the equals method. Okay, let's now take a look at this one here. So this is the closest, I should say closest ancestor overriding the equals method. Hypothetically, let's say that could be exercise number 4, which I didn't have. Let's say we override the equals method here. We also override the equals method here as well. In that case, when we say C1 equals C2, are we going to invoke this version over here, or this version here, or this version here? The answer is only this version, because the closest. That's the principle. This one, even though it is also overridden for the equals method, but it's actually further from this ancestor. So that's why this is not going to be called. All right. The closest is really the key. Okay, so that's about the 3 exercises I want to speak about. So this one should be just B, right? You can see the version that's going to be called will just be B over here. Okay, I believe in the previous one it's actually C, right? Okay. Okay, let's now go back to the slides. And so that's the examples I just spoke about, right? You can see example number 1, example number 2, example number 3 here. And the next, the last topic is about the toString method. Let me just remind you very quickly. We have learned about it a long time ago, but I just want to put that into this context over here. So if you simply got some point class and P1, and let's assuming that you haven't overridden the toString method in the point class. If you simply try to print it out, P1, you will only get the address. Of course, in Eclipse, you also get a package as well. But the idea is you only got the address without any meaningful contents in the toString method. Implicitly, the toString method is called inside the print line method. Oh, so here, that's also what we said in the review tutorial. If you only put P1 here, implicitly, you're really calling P1 the toString. That's what this line is saying. Okay? And then, by default, only the address stored in P1, the reference variable, will be printed out. And we need to, if you really want to print out something useful, you want to override or redefine the toString method. Okay? So let's say, for example, here, I can say in the point class, I say public string to declare that, and then I just put something meaningful to override the behavior, rather than just printing out the address. That's something we spoke about in the review tutorial, and also your lab solution walkthrough. Okay. Okay. After you redefine, after overriding the toString method, what you will see is something that's meaningful rather than just the address. But of course, sometimes you might still prefer the address of the printout. It's up to you. Okay, but I think most likely you will want to override the toString method. Exercise for you. You want to reproduce the example for resident students and also non-resident students that we did in the lecture. And you want to override the equals method and toString method to play with them. Okay, to see how you can redefine them, override them. Okay. All right, finally, what should you do beyond this lecture? It's a very giant topic about inheritance that we have spoken about. I'm reasonably confident I cover almost everything in the clearest way I can. There might be some imperfection, in which case you can definitely reach out to me to explain for you. But I think the next part has to be done by you, which will be, let me list them. You want to implement the inheritance hierarchy for the student example, right? Only 3 classes. And then reproduce all the lecture examples about compilation, about variable substitutions, about typecasting, about instance of, and about method parameter, and etc. Right? That's something I want you have to do it. And also implement the inheritance hierarchy of the smartphones example as well. That one is actually more complicated, right? But we spoke about how you can do it, so you definitely should do it. And hints will be pay attention to whether or not a line is actually valid or invalid, whether or not it compiles or not compiles. And also in the case of typecasting lines, you want to make sure you understand whether or not there will be some class cast exception, right? Remember the 4 categories we spoke about last week. Finally, I will make available one exercise example for you. Okay, let me show to you. So you can download this zip file for the project example typecasts over here. I put simply A, B, C, D, E, F. Okay, so these are the likely symbolic nature of your written test or your exam. Okay, so it's that would be the best chance for you to practice. If you go, you can see, for example, class A, class B, which extends some other class, right? I say based on the class example, based on the class declaration over here, I want you to first of all do the following. First of all, I want you to really draw the inheritance hierarchy diagram, and then you can experiment with the various substitution and cast over here. I already included some example code for you over here, and also with some explanation. You can play with them, okay, and convince yourself that's really gonna happen, right? And about class cast exception, or maybe no class cast exception, or maybe the cast will compile or not to compile, right? You can definitely extend the tester by including more example on your own to play with the different rules that we spoke about in the lecture. All right, so that's about what I want to say about the inheritance lecture. I hope you also find the topics interesting, and you will really be worthwhile your time to actually dive into the topics and think about the issues. That will definitely help your understanding for advanced OOP. All right, that's about it. If you got any questions, reach out to me. Stay tuned.